Okay, so let us start. Good evening and welcome to today's Asset Colloquium, which is titled as an overview of the Global Navigation Satellite System, GNSS for short. One of our colleagues from balloon facility of TIFR Hyderabad is going to deliver this talk, Mr. Venkateswara, Tanneeru. In fact, these talks are going to be two. One is today and another one is going to be on 28th of April. Of course, today's talk had to be preponed because tomorrow's is declared as holiday. So otherwise it would have been tomorrow. Let me briefly introduce today's speaker. Mr. Tanneeru Venkateswara is actually, for all of us, in short, he's called TIFR. He's our colleague working at balloon facility of TIFR Hyderabad since the year 2000. Right now he's a scientific officer, and he takes care of designing and developing onboard and ground-based telemetry subsystems and also satellite-based navigation subsystems. He did his ME/MTech degree from Usmania University, Department of Electronics and Communication Engineering, in the specialization of digital systems engineering. That was in 2015. And in fact, currently he is pursuing his doctoral degree from Tanneeru Lakshmiya Education Foundation in Andhra Pradesh, and his field of in the field of ionospheric studies. His other research interests include GPS, Global Positioning System, amplitude scintillations correlation analysis, scintillations prediction, and mitigation algorithms to improve positional accuracies during scintillations period. In fact, his second talk is going to be more on some of these aspects, but today is going to kind of giving us more of an overview and introduction to global navigation satellite systems. So over to TIFR.
Yeah, thank you so much for the nice introduction, sir. Hope I am audible to everyone.
Yes.
Okay. My name is TIFR, and I am working at balloon facility of TIFR Hyderabad. And in this session, I'm going to discuss about overview of global navigation satellite systems. So, good evening to everyone. So this is the overview of my presentation. I will start with the introduction part. I will discuss about satellite-based navigation system architecture, GNSS systems, applications of satellite-based navigation systems, and the applications of satellite-based navigation systems in balloon-borne scientific experiments. And I will conclude with the summary. So I will start with the introduction part. This is the fundamental problem that one should know his position on Earth, that is where I am on Earth, and how to navigate from one place to the other place in a shortest path in a proper direction. That is how to know my location precisely in any condition at any point of time everywhere on Earth, and how to navigate from one place to the other place. These are the two fundamental problems. For that, we have various navigation systems. These are the navigation types we have. See, in earlier days, in olden days, we used to navigate or travel from one place to the other place using landmark-based navigation system. Means we used to have stones, means reference stones as well as trees and monuments. Using this landmark-based navigation system, it is limited to the local use only, because the stones, reference stones or trees available locally. So coming to the celestial-based navigation system, so based on the star constellation, moon, and so on. So one is to travel from one place to the other place, means navigating from one place to the other place. So coming to the celestial-based navigation system, it is a bit complicated because one should know and one should understand the know the constellation of stars and moon and so. So this is the satellite means celestial-based navigation system works only during the night time, or that too during the clear nights. The other navigation system is the sensor-based navigation system, where it consists of the IMUs, inertial measurement units, that is cope up with the along with the gyroscope, accelerometer, and magnetometer. So the current position will be derived with the help of previous position, which is called the dead reckoning. So with the in the case of sensor-based navigation system, so one is to travel or one is to navigate from one place to the other place. So the sensor-based navigation system or the IMU-based navigation system is a little bit complicated in deriving the current to position because of the less accurate gyroscope, accelerometer, and magnetometers, and there is a possibility of accumulating errors when you use IMU sensors. So that is about the sensor-based navigation system. Coming to the radio-based navigation system, in this system, the high-rise towers will be installed at different places, and the communication signals, RF signals, will be transmitting from each towers, and that will be identified with that. One is to derive the position, one is to navigate from one place to the other place. So these are the examples of radio-based navigation system, that is LoRaWAN and Omega. And this system is subjected to the radio interference. Means there is a problem with the radio-based navigation system, that is interference and jamming issues are there in the case of radio-based navigation system. And it is limited with the coverage. Means if you want to have wide coverage, we have to install the towers specially. So that is the limitation of radio-based navigation system. And coming to the satellite-based navigation system, so it is developed, designed for providing the global navigation services to the users. So these are the examples: GPS, GLONASS, Galileo, QZSS, IRNSS, and Compass. These are the examples of satellite-based navigation system for giving the global as well as the regional navigation services to the users. And the benefit of using satellite-based navigation system is it is difficult to interfere or jamming. And with this system, we will have high accurate navigation parameters. At the same time, we will have the user position in with high reliability. So these satellites are placed at MEO orbit or geostationary orbits. And these are about navigation types. So coming to the constellation, so any satellite-based navigation system constellation means architecture consists of the three segments. That is the space segment consisting of the satellite vehicles, control segment, that is the ground segment consisting of the antennas, monitoring station, and commanding stations. And the third segment is the user segment consisting of the receivers for receiving the signals which are being transmitted by the space segment. That we will discuss. Coming to the space segment, as I indicated in my previous slide, it consists of the constellation of satellites which are transmitting the radio signals along with the navigation parameters to the user segment. And these satellites are placed at the medium Earth orbit, MUO, at about 20,000 kilometers height, and geo orbit, geostationary orbits at about 36,000 kilometer height. Coming to the control segment or the ground segment, it consists of the network of ground antennas where the signals are being received, and network of globally distributed monitoring stations where they are computing the range parameter and extracting the navigation signals or navigation parameters from the received signals. In case of any errors found, that information will be given to the master control station for making or for generating the error corrected navigation message, which will be transmitting again to the space segment for corrections. These are the functions of the ground segment or control segment. And coming to the user segment, generally consisting of dual frequency receivers or single frequency receiver for military as well as the civilian applications. Coming to the space segment, as I indicated, it consists of the constellation of satellite. So each satellite consists of 2 to 4 atomic clocks of cesium or rubidium for getting the high accurate clock information about 1 in 10 to the power of 11 and 1 in 10 to the power of 12 clock accuracy. And they are satellites are equipped with the solar panels for generating the power requirement for the onboard segment. It is about 1000 to 1400 watt the solar panels are generating. And it has batteries. So batteries are getting charged during the daytime with the help of solar panels, which will be used for powering or giving the power during the night times to the onboard segments. And it will be having S-band antennas for command, for satellite control operations for the command stations. And there will be S-band antennas, L-band antennas for user communications, means satellite data or navigation data will be transmitted to the user segment on L-band signal with the help of L-band antennas. Coming to the signals, so at the end of the satellite, each satellite, there will be a carrier signal. So in the case of satellite-based navigation system, generally they use 2 carrier frequencies to overcome the ionospheric errors, means to correct the ionospheric errors. So in the case of GPS, they use L1 and L2 carrier frequencies. And in the case of GNSS, they use L5 and S-band carrier frequencies. And there will be a ranging code, means PRN code, pseudo-random noise code will be given to each and every satellite for identifying the satellite from which the signal has been received. And there will be navigation data, which consists of the satellite health parameters, ephemeris, clock bias parameters, and satellite vehicle constellation almanac parameters, etc. And these navigation data is embedded onto the ranging code, and that will be modulated on carrier, and that will be transmitted to the towards the user segment. And this is how the signals are being modulated. So this is the base clock or the fundamental frequency is derived from the atomic clock, which is working at 10.23 megahertz. In order to generate L1 carrier frequency, this fundamental frequency is multiplied with 154 times. And in order to generate L2 carrier frequency, this is in the case of GPS constellation. So to generate L2 carrier frequency, so the fundamental frequency 10.23 megahertz is multiplied with 120. The L2 is 120 times. So if you multiply 10.23 megahertz 120 times, you will get L2 carrier frequency. So as I indicated, this navigation data, which is varying at 50 Hz, will be embedded onto the PRN code. So this PRN code is assigned to each and every satellite. The PRN code will be different for each and every satellite. So this navigation data is embedded onto the PRN code, which is chipped at 1.023 megahertz. And this embedded signal will be modulated on L1 carrier frequency, which is in-phase signal. At the same time, the navigation data, which is embedded on P code, the P code is of the PRN code, which is chipped or shifted serially with the frequency of 10.23 megahertz. This navigation data, which is embedded on P code, will be modulated on the same L1 carrier frequency with the phase shift of 90 degrees. This is C by A code. The navigation data embedded on C by A code is modulated in phase of the L1 carrier frequency. The navigation data embedded on P code will be modulated on the L1 carrier with the 90 degrees of phase shift. These two modulated signals are combined, and that will be transmitted towards the user segment. At the same time, the P code, the navigation data embedded on P code will be modulated on L2 carrier frequency in the case of GPS constellation, and that will be transmitted towards the user segment. So in principle, in the case of GPS constellation, we have 2 carrier frequencies, L1 and L2. And we have C/A code, PRN code, chipped at 1.023, which is called C/A code, course acquisition code. And the PRN code, which is chipped at 10.23 megahertz, is called precision code. If we encrypt, that will be called as P of Y code, that is encrypted precision code, which will be chipped at 10.23 megahertz. And these signals are being modulated on L1 as well as the L2 carrier frequency, and those signals L1 and L2 carrier frequencies are transmitted to the user segment. So this is how the signals are transmitted from the onboard segment or the space segment towards the user segment. Coming to the control segment or ground segment, we have, as I explained in the previous slide, we have network of ground antennas for receiving the signals which are being transmitted by the space segment satellites, and it has a network of globally distributed monitoring stations, and it has the master control stations. It receives the signal, and the monitoring station will compute the ranging parameters. It will extract the navigation parameters from the received signal. In case of any errors found, like clock errors, in orbital parameter errors, or in case of any almanac errors, this message will be given to the master control station for generating or for making a or for creating a navigation message of corrected information that will be again retransmitted to the space segment for corrections. This is about the control segment. And coming to the user segment, so typically the receivers are dual frequency receivers. In case one can have the single frequency receiver also. In order to have the ionospheric corrections, we should have the dual frequency receivers. So typically all the receivers are dual frequency receivers, and this is the typical architecture or typical block diagram of the receiver, where it has an antenna part, and the front end part, which will be converting the RF signal to the intermediate frequency signal. And there is a acquisition block for acquiring the satellites in view, and there will be a tracking loop for extracting the navigation parameters from the received signal, and there is a block for computing the user position. So we have two types of antennas, that is active antenna as well as passive antenna. So most of the time, active antennas are used for having the better sensitivity, and in the user position computation block, user parameters are computed. So the functions of user segment or the receiver are processing the signal received from the satellites, and it will identify the number of satellites in view, and it will estimate the user position. So this is about the user segment. And coming to how the user position is estimated. So in the satellite-based navigation system, they use the trilateration or triangulation principle for deriving the receiver position or the user position. The distance of unknown point from the three known points are measured, and the intersection of three satellites, the arc means the three arc defines the unknown point related to the three known points, satellite points. So ranging will be calculated. So this is how the range parameter is measured. So this is the signal where the satellite is transmitting at time t, and this is the signal received at the receiver with the t plus time. So range information is measured from each and every satellite. So to derive the user position, we require at least 4 satellites, as we have 4 parameters, that is latitude, longitude, altitude, along with the bias parameter. So in order to compute 4 parameters, we need to have at least 4 satellites to provide 3-dimensional user position to the user. And these are the functions to compute the user position. Coming to the signals for ranging, so we have 2 signals. As I said, we are getting the carrier frequency from the out of the satellite, and inside that we have the PRN code information. So we have 2 signals for calculating or for determining the range between the satellite and the user. So that is the carrier and PRN code. Using the carrier, they measure the carrier phase measurements for deriving the range parameter. And using the PRN code, they will derive the, means one can derive the range between satellite and user using the code phase measurements. As I said, we have two signals inside the PRN, inside the carrier frequency, that is C by A code, which is chipped at 1.023 megahertz, and P code, which is chipped at 10.23 megahertz. So these two these signals are used for deriving the range between satellite as well as the user. So with this C by A code, one can derive the standard position services, that is SPS services, which will be given or which will be for civilian applications. And using the P code, the ranging data extracted or ranging parameter extracted or derived will be of the precision position services, that is PPS services, which are for the military applications. So coming to the need of multi-constellation. So what is the need? Why do we need multi-constellation if one is providing the global coverage? So when the safety of the life comes into the picture in the case of civil aviation applications, so it is very important to have the user position continuously without losing for a fraction of a second in the case of civil aviation application. If we rely on the single constellation, there is a possibility of selective availability, means one can derive the user position from the satellites available or from the signals which are available from the satellites. If we rely on single constellation, there is a possibility of intentional dithering or intentional not serving the services to the users. So that makes the problem in the case of safety of the life, in the case of the civil aviation applications. To overcome that, so one has to go for multi-constellation, and at the same time, for computing the user position, three-dimensional user position, one should have at least 4 minimum satellites. So, but because of the ionospheric errors, because of the tropospheric errors and multipath reflections, the signal is getting degraded. The signal maybe means there is a possibility of degrading of the signals. In that case, there is a possibility of losing the continuity in tracking the satellites. So if we rely on the single constellation, there is a possibility of losing the user position. There is a possibility of degrading the user position if we rely on single constellation. That is the reason for going for the multi-constellation, which is called the GNSS. GNSS is nothing but a global navigation satellite system, means bringing all the constellations under one roof is nothing but the GNSS, where GNSS system has the constellations of GPS, Global Positioning System, GLONASS, Galileo, Compass, QZSS, and IRNSS. So these are the constellations for providing global as well as the regional coverage. United States of America is maintaining GPS, GPS Global Positioning System constellation for providing the global coverage. Russia is maintaining GLONASS constellation for providing global coverage, whereas Galileo is developed for global coverage maintained by Europe. Whereas China is developed and maintaining the Compass constellation for getting the global coverage. Coming to the regional coverage, Japan has developed QZSS, that is Quasi-Zenith Satellite System constellation with the satellites for regional coverage to the users. At the same time, the government of India developed and ISRO is maintaining that India has developed the Indian Regional Navigation Satellite System, that is IRNSS, or the navigation with the Indian constellation, and that is for providing the regional navigation services to the users. Let me start. Let me describe about the global positioning system, which is maintained by USA. This is the history. This GPS is originally started, means they have started with for providing the military applications. And in the year 1960, they have launched the first satellite called Transit. And during 1978 and 1985, they have launched 11 satellites with the intention of providing the global services, navigation services to the users. And by 1995, they declared that GPS is giving global navigation services to the users. And right now they have about 32 satellites in the orbit, from which 31 satellites are active. And the GPS is used for navigation applications, most of the devices right now. So this is about the onboard segment, means space segment, ground segment, and user segment. So as I told, it has about means basically the GPS has planned with 24 satellites for global coverage, and right now they have 32 satellites in the orbit, 31 are operational, and remaining apart from 24, remaining satellites are kept as a standby or the spare, and they have placed these satellites in 6 circular orbit planes, 4 satellites in each orbital plane. And these are the orbital parameters. It has a circular orbit, which is at 20,180 kilometers height. And each satellite is placed with inclination of 55 degrees. And these are the services provided by GPS, open and authorized services. Open services for civilian applications, authorized services for military applications. And coming to the control segment or the ground segment, it has the network of ground antennas for receiving the signals. It has the network of monitoring stations for computing the range between the satellite and the user, and extracting the navigation parameters from the received signal. And in case of any errors, that message will be given to the master control station for generating or for creating the navigation data, error corrected navigation data, which will be transmitted to the space segment for correcting in the space segment equipment. So coming to the receiver, as I indicated in my previous slides, so the GPS is designed with the L1 as well as the L2 carrier frequency. So the user segment or the receivers are equipped or designed or developed with the dual carrier frequency receiver for computing the user position. So coming to the GLONASS, which is maintained by Russia. So this is about the space segment. They have planned with the 24 satellite initially, and right now they have 26 satellites in the in 3 orbital planes, 8 satellites in each plane. Right now they have 26 satellites. Apart from 26, 23 are operational, and the orbital these are the orbital parameters: circular orbit, which is at 19,130 kilometers height, and each satellite is placed with the inclination of 64.8 degrees, and they are revolving at the time of 11 hours 15 minutes every 11 hours 15 minutes. And these are the 2 services which are provided by the GLONASS. That is open service, that is standard for civilian applications, and the second one is authorized services for military applications. So coming to the control ground segment or control segment, they have the network of antennas, they have the network of monitoring station, and they have the master control station for commanding operations. Coming to the receiver, here I will mention one point, that there are 2 techniques called CDMA technique and FDMA technique, which I will discuss in the next slides. So GLONASS is developed with FDMA techniques. FDMA means a frequency division multiple access system. So each satellite will be identified with different frequency. One satellite with one frequency, the other satellite with other frequency. So FDMA technique is used for GLONASS constellation. So the receivers also equipped, receivers also developed to accommodate the FDMA technique for retrieving or for extracting the navigation parameters for computing the user data. So we will so again we will discuss about Galileo, Europe. These are the space segment parameters. So initially means they planned for with the 24 satellites for global coverage. Right now they have 30 satellites in orbit. So they placed the satellites in 3 orbital planes, 8 satellites in 3 planes. Means each plane, the 8 satellites in each plane of 3 orbital planes, and 2 spare satellites are available in each plane. So this is the circular orbit, which is at 23,222 kilometers height, and each satellite is placed at 56 degrees inclination. And these are the services the Galileo is providing to the users. Open service, that is standard for civilian applications, high accurate services for military applications. And apart from these two, the general 2 services, they are also providing search and rescue services with the help of satellite-based navigation system. Means with that constellation for disaster management services. So coming to the compass, China. So they quote means they say they indicate that they have the 27 MEO satellites, 27 satellite placed at MEO orbit, and they have 3 inclined geostationary, means geosynchronous orbits. Means they place 3 satellites at the inclined geostationary geosynchronous orbits, and they have placed 5 satellites at geostationary orbit, which is about 36,000 kilometer height. And coming to the ground segment, they have master control station, uplink station, that is commanding station, as well as more network of monitoring station. And coming to the user segment, they have 12 frequency receivers for receiving the signals and computing the user position. And they are providing the 4 types of services, that is open for civilians, authorized services for military applications, and differential augmentation for improving the positional accuracy. And the other services, which the video or compass is providing is short message service, SMS services, using the satellite-based navigation system. And they also quote that they can provide the positional accuracy of 10 meters, and the timing of 20 nanoseconds, and the velocity accuracy of 0.2 meters per second. Coming to the QZSS, so far we have discussed about the global coverage. Now we will discuss about the regional coverage. The QZSS maintained by Japan. Initially, they planned the regional coverage with the 7 number of satellites. But right now they have 5 satellites in the orbit. The first satellite was launched in 2010, and the last 5th satellite was launched in 2021. And they are providing the services, means navigation services like open for civilians, authorized for military applications. They also provided, means other features which QZSS is providing to the users is the QZSS constellation is interoperable with the GPS, which is similar to our Gagan, where Gagan is the GPS aided geo augmentation navigation system. So similar to the Gagan, so the QZSS is also interoperable with GPS, and they also provide the augmentation data for high accuracy. And last but not least, the Indian constellation, that is Navig, navigation with Indian constellation Navig, which is maintained by India. So this is the details of IRNSS. In the space segment, we have 7 satellites, means the proposal was to have 7 satellites for regional coverage. 3 satellites are placed at geostationary orbit, and the 4 satellites are placed at geosynchronous orbits. And these 3 satellites are placed at 34 degrees of east, 83 degrees of east, and 132 degrees of east, approximate height of 36,000 kilometers. And these 4 geosynchronous satellites are placed with the inclination of 29 degrees which is crossing longitudinally at 55 degrees and 111 degrees of east. And with this IRNSS, they are providing the services like standard and military open and authorized services. And coming to the user segment, this is also dual frequency receiver. So I forgot to tell you, the IRNSS is transmitting the signals on L5 as well as the S-band signal. L5 signal is derived from the fundamental frequency of 10.23 megahertz. If we multiply 10.23 megahertz with the 115 times, means 10.23 into 115 times, you will get L5 frequency and 2.4 megahertz of S-band. So the signals are being transmitted on L5 as well as the S-band signal. So the receivers, means the user segment, also developed, means designed to receive dual frequencies for computing the user position. At the same time, coming to the ground segment or the control segment, we have a network of antennas for receiving the signals. We have network of the monitoring station for calculating the range between the satellite and the user, and for extracting the navigation parameters from the received signal. In case of any errors, that will be given to the command control station for generating the navigation error corrected navigation message, which will be transmitted to the onboard section for correcting the errors in the onboard segment. So coming to the applications of satellite-based navigation system, here nowadays, means in this situation, in every sector, the satellite-based navigation system is being used. So these are the basic applications. So in the satellite-based navigation system are used in timing applications for giving the precise timing information, and surveying and mapping in the sector of agriculture, in disaster management or disaster control sectors, in the transport sector, road, railway, marines, and aviation, etc. And also the satellite-based navigation systems are used in scientific ballooning. So we'll discuss about the implementation of satellite-based navigation system in conducting the scientific experiments, and the importance of GNSS. So at our balloon facility, means at our balloon facility of TIFR, we are supporting for conducting the onboard scientific experiments with the help of plastic balloons in the areas of astronomy, that is X-ray astronomy, gamma ray astronomy, far infrared astronomy, and atmospheric sciences and astrobiology. So for providing the coordinate information and providing the precise timing data to the scientific payload, for synchronizing onboard equipment as well as the ground-based equipment, and at the same time for providing the navigation data during the course of the balloon flight, for tracking the balloon as well as tracking the payload after the termination, we are providing, or we are using, the satellite-based navigation system in the onboard section. Let us see the importance of GNSS, application of GNSS systems in the scientific ballooning. So in the past, we had an experience that during the Kargil war, if I am not wrong, during the Kargil war, we have conducted a balloon flight where we could not get the precise balloon information because during that time, United States of America, USA, intentionally deterred the signal levels. So that makes us to recommend the GNSS. Means at that time we have used only single constellation. So that makes us selective availability. So to overcome the selective availability, and at the same time, if we rely on the single constellation, there is a problem of degrading the signal because of the ionospheric or tropospheric errors, which will degrade there is a possibility of degrading the signal, where there is a possibility of losing the continuity in tracking the signals if we rely on the single constellation. There recommends us to use the GNSS multi-constellation receivers multi-constellation techniques in the balloon-borne experiments for providing the coordinates and timing information, which is crucial for the scientific payloads, and navigation information for tracking the balloon during the course of experiment and tracking the payload till touchdown point after the termination of the balloon flight, for recovering the scientific payload safely and handing over it to the user scientist after recovery. So recovery is also one of the prime aspect of the scientific balloon that makes or that recommends the GNSS receivers in our balloon flight. So these are the various payloads which we launch from the balloon facility. This is the LACE payload, exit payload, LAX PC, and far infrared astronomy from the TIFR headquarters. And this is the astrobiology experiment of ISRO, and this is the bird experiment from the PRL Ahmedabad. So depending on the requirement, means height requirement and weight requirement, we manufacture in-house, we manufacture the balloon as per the height as well as the weight requirement, and we provide the launching support from balloon facility for Hyderabad. So as I said, we provide the satellite-based navigation system in the onboard section. So the navigation parameters are being transmitted to the ground station on the telemetry channel. After receiving the signals at the ground station, we will decode and we will extract the navigation parameters, which are continuously or online we are displaying for the taking the necessary actions. And at the same time, we also plot the navigation data on the Google Maps during the course of the flight. And once the experiment is over, we see the good terrain using this navigation parameters. We see the good terrain for a termination of the balloon flight for recovering the payload safely back to the facility, which is the prime aspect of scientific ballooning. So once the experiment is over, we terminate the flight. So the scientific payload will come with the help of the parachute. So the touchdown point will be intimated to the recovery team, where the recovery team will go to the touchdown point and they will recover the scientific payload back safely back to the facility. That will be given to the back to the user scientist. So as I told in the previous slides, so, and by that time, one should have the question that how to identify so many number of satellites, because each constellation is having about 20 to 30 satellites, and we have multi-constellation, the combination of multi-constellation. So we have n number of satellites, more number of satellites. How to identify each and every satellite? So there comes the techniques called CDMA, that is code division multiple access system, and FDMA is the frequency division multiple access system. So the GPS, QZSS, Galileo, Compass, and IRNSS are following the CDMA technique, whereas the GLONASS, Russian people, they are always opposite to the US people, that is GPS. So if the GPS is using CDMA, the GLONASS Russian people are using FDMA technique. So each and every satellite, in the case of CDMA, each and every satellite will be identified with a different PRN code, pseudo random noise code, that is gold code in the case of CDMA, whereas in the case of FDMA, each satellite will be identified with a different frequency, that is from central frequency to the different frequencies. So in the case of CDMA, frequency is 1, either it could be L1 or L2. In the case of FDMA, the different frequencies for different satellites are used. And these are the merits and demerits. In the case of CDMA, the receiver design is simpler. In the case of FDMA, receiver design is a bit complex. And in the case of FDMA, there is a inter-channel interference will be there because of the multiple frequencies, and because of the FDMA, it is less susceptible to the jamming. And in the case of CDMA, it is more susceptible for the jamming, and there is no interference because of the single frequency or dual frequency. This is about CDMA and FDMA. So this is the summary. So far we have discussed about the GNSS constellation. So GNSS is proposed, the multi-constellation is proposed to overcome the selective availability issue and continuity issue in computing the user position. And these are the multi-constellation comes under GNSS, NAVIC, maintained by India for regional coverage, which is using the CDMA technique for giving the positional accuracy of 1 meter to public, 0.1 meter to the military applications. And GPS is maintained by USA for global coverage using the CDMA technique, placed at 20,000 kilometer odd altitude for providing the 0.3 to 5 meter accuracy to the users. And GLONASS is maintained by Russia for global coverage, which is using FDMA, and future GLONASS constellation are using CDMA technique, which are placed at 19,000 odd kilometers for providing 2 to 4 meter accuracy to the users. That is about the summary. And last, finally, so the satellite-based navigation systems are developed or means proposed to provide meter level and centimeter level accuracy, even though the satellite-based navigation systems are there for providing meter level and centimeter level accuracy. The differential GPS concepts are brought to have better accuracy. Multi-constellation concepts are brought to have better accuracy by overcoming the selective availability as well as the continuity. And system augmentation system are recommended for correcting the errors to improve the positional accuracy. And there is a wide research work is going on for improving the positional accuracy to get meter level and centimeter accuracy. My question is, why wide research work is still going on to achieve meter level and centimeter level accuracy, and where the accuracies are getting suppressed or inhibited is the next topic which I am going to discuss in the next colloquium, asset colloquium, which is scheduled on 28th of this month. Thank you.
Thank you, Tivra, for a very nice overview of, and not only just overview, but also you touched upon some of the technologies and applications, and of course, also the work by your team and your group, besides the other work that is happening in India. There will be some questions. So any of participants want to ask questions from Zoom, please feel free to.
Can I ask?
Yeah, please, sir.
TV, couple of points maybe I missed during your talk. One was did you explain that what was the advantage of going from L1 to L5?
Okay.
And the second, just a minute.
Sir.
And say, now since you have said you are giving one more colloquium, my question was going to be actually, what is the effect of TEC in overall error of the height measurement, and why a real-time model for TEC is necessary to make good use of it?
Yes, sir. That I will touch in next colloquium, sir. Definitely with the calculations and all.
That is my guess that you will be talking on that.
Yes, sir. Yes, sir.
So
because I don't want to. Yeah.
So L1 to L5, you can explain what is the advantage.
So L1 to L5 means the GPS is having L1 and L2, and going from L1 to L5 is to have the positional accuracy, improvement in the positional accuracy, because as the frequency increases or the frequency band increases, the effects of the ionosphere on the different range of frequencies will vary. So that is the main advantage. And the second the problem or the constraint of using L5 is the getting the band, the particular band to the users.
So you should maybe next time show the figure of fading paths.
Sure, sir. Yes.
Because otherwise it doesn't become clear what advantage one gets by moving the frequency.
Frequency to the other.
Apart from bandwidth, of course, that is a small gain.
Sure, sir.
Okay.
Sorry, I must have missed. What is the frequency of L5?
1175, if I'm not wrong, that is the multiplication of 115 times of the fundamental frequency of 10.23 megahertz.
Okay, so it's less than L2. L2 you said is 1200.
I think 1175, sir, L5, if I'm not wrong.
1175.
Yes.
Okay. Yeah.
So anything is multiplied with the fundamental frequency.
Fundamental.
Yes. Which is 1176.45 megahertz, sir. L5.
Okay. So Manchanda sir's questions, did you all answer other than what you are postponed to?
Well, I will postpone because now TEC is the more important part, which is.
Yes, sir. I will touch.
He just announced that he is going to talk next.
Yes, sir. Yes, yes, yes.
All right. Okay.
Just I have mentioned a single point that utilization of the two carrier frequencies for having the ionospheric error corrections.
Yeah, that's the differential mode, basically.
Yeah, the differential mode. And in my next slide, I will indicate where the errors are, as I said, where the accuracies are getting suppressed. So ionosphere is the main component which is affecting the positional accuracy. That I will discuss, and I will tell you how the positional accuracy is getting degraded and what measures we have to take to improve the positional accuracy.
Okay.
And prediction analysis, yes, I will try to indicate the prediction analysis in ahead of 1 hour or 2 hours or 24 hours, and what precautions one can take. That I will try to explain in next colloquium, sir, definitely.
Okay. Any other questions from Zoom audience?
Yes, if I may.
Yeah, please go ahead, Alec.
Very nice talk. I have missed a part of your talk because I was late. So I'm just wondering if you would explain one thing, and then I have also other questions.
Sir.
You know, what is really the advantage of the
constellation?
Yeah, multi-constellation system as opposed to the single constellation system. And you said earlier GPS were primarily single constellation systems. So that's number one. And number two, I was surprised that the GLONASS system, which is used by the Russians, is as inaccurate as 2 to 5 meter accuracy. Is it really right? Because they're using a lot of cruise missiles which in Ukraine which are apparently dependent upon satellite navigation. So if you have such poor resolution, how can they actually be effective military? And the last set of questions I have is that
Alec, maybe if you don't mind, can you complete these couple of questions and then maybe you can ask next?
Sure.
Yes, sir. First, I will answer the second question. That GLONASS is giving the accuracy. So here, two parts are there: civil applications and military applications. For military applications, they use the precise code or the precision data for giving better accuracy when compared with the civil applications. So, that is different, sir. Military applications, they get very precise data in even centimeter level accuracy. And coming to the first question, may I know the first question again, sir?
The multi-constellation.
Yes. Because if one relies on the single constellation, let us take an example of GPS. If we rely on the GPS constellation, if he intentionally stop the services, then how do we get the user position? It had happened to us during the Kargil war. So during the Kargil war, they stopped the services and they literally deter the signal quality to get pure poor accuracy, and even we could not get the exact positions. So if we rely on the single constellation, that problem is there. That is called selective availability. And the second one is to have the continuity in tracking the 4 number of satellites for computing the user position. If we rely on the single constellation, because of the ionospheric errors, because of the disturbances in the ionosphere, where TEC comes into the picture, there is a possibility of losing the track of 4 minimum satellites. In that case, if we rely on the single constellation, there is a problem in getting the user position. The user position is very, very crucial in the case of civil aviation application, where the safety of the life comes into the picture. That recommends to go for multi-constellation, sir.
Okay.
Okay, can I ask another question?
Yes, sir.
Yeah,
Yes.
please go ahead.
Yeah. So many of these, several of these frequencies are in bands which are, used in radio astronomy. So, and we do know that there are some US satellites which really quite severely affect GMRT, for example, observations. So the fact that you are having so many satellites and many of these frequencies are utilized, which are smack in the very effective frequency range of GMRT observations. How do you take care of these astronomical needs versus the positional and military needs on one in the radio astronomy side only? And of course, we have seen pictures of photobombing satellites of beautiful Hubble Space Telescope images. So, I mean, that is, of course, in a different part of the electromagnetic band. But as far as the radio bands are concerned, how is this to be, coordinated?
So what is this single point question, sir? How to
avoid interference with astronomical observations?
Okay.
May I answer this?
So, yes, sir. You can, or we can have the filters to avoid these frequencies.
No. Shall I answer that?
Please, sir. Please.
See, that what you are Alak saying is the carrier noise. In this case, we are talking of the position which has been coded into the carrier.
Yes, sir.
And when basically that carrier is nothing but a noise. But we're using a algorithm and the known information of what kind of code is going to be there, you extract it. So that poorness of the data extracted is different than the integral carrier noise on a dish from a variety of transmitters which are transmitting above. So these two things are a bit different.
I'm not fully sure whether it really answers my question, because I do know that there are certain satellites, I mean, not in the L band, but other bands, which really create a lot of problems. And even if you know the frequency ranges and you excise them, there are harmonics of it which pollute a large part of the band. So I don't know whether it's so easy to actually weed that out by just RFI techniques, radio frequency interference excising techniques. So I wonder whether, these are being looked at by our people in the radio astronomy community. I'm sure that they are.
Okay, sir. I will check for the answer and I will come back to you, sir.
Sorry, I had to take a sudden call from director's office. Can I call you this? Sorry, that was something an urgent call, so I couldn't avoid. Are there any more questions? I hope Palak is happy with Dr. Manchanda's explanation.
Maybe we have to discuss this later.
Okay.
Yes, sir.
Okay. Any other questions from the Zoom audience? I have one question from YouTube. I'm not sure how it gets related directly, but of course it is about GNSS. So the question is from Abhinav Chaudhary. It says, do GNSS need internet services for accurate reading? So do you have an answer for this?
Internet service for accurate readings.
Yeah, this is from YouTube, so you may have to kind of think if this is something out of the scope of your talk. Also, to me, it is not clear how these things get connected in the question.
So I will look into that, sir. Question.
Okay,
If you just post me that, I will try to answer that.
Abhinav, you can kind of, if you
Yes.
are there on the YouTube, please give a little, more details about what you're asking. Then the speaker will be able to kind of answer you. Meanwhile, I just want to ask once again if there are any questions from the Zoom audience. Okay. So TIFR, I don't see any more questions. So on behalf of all of us, I'd like to thank you for your very nice lecture. We also very much look forward to even more interesting maybe, because I think that is the kind of topic that you're currently pursuing for your PhD.
Yes.
So we look forward to your next lecture that is on 28th April.
Yes.
So thank you. Thank you once again. Thanks all of you who have joined the Asset Colloquium. Thank you.
Thank you so much, everyone.